Hello, it is Friday, the 23rd, and I just wanted to spend a few minutes here and let you know within an hour or two, supposedly I'm going to be released from COVID jail, and I'll be back in class on Monday. But I just wanted to talk real quickly for a few minutes about probability functions, and we'll go into greater detail again next week. Sorry, this is probably pushed back just a little bit, but we'll try to keep up. Okay, in probability functions, what we have is we are writing down what we know the states of nature to be. Okay, so in a little bit, I will upload a picture of Polly playing one of her favorite games, which is flipping the coin. And as I kind of mentioned in that case, we sort of know that just from the dynamics of how a coin operates, that the chance of getting a head is 50%, the chance of getting a tail is 50%, and the chance of getting anything else is zero, right? Those are the two options. Yet, even though we know the state of nature, Polly loves playing this game. He loves going onto the table, taking a bunch of pennies, pushing them off one at a time, and then jumping down to see whether it landed as a head or a tail. And then she'll go back up and do the next one, right? So for a cat, this is a very entertaining game to play, even though the cat probably knows that the odds are 50. So in that realm, what we're going to do is we will have a probability function. And a discrete probability function is essentially a histogram. So we have a histogram with heads and tails, with each one being equally likely. And again, I think I used a color that did not work very well. So let me see if I can find a black color. I can figure out what I did with there. So essentially we have a histogram. There, that seems to show up better. Okay, and in a probability function, one of these that we call a discrete probability function, okay, it is a series, it's a histogram. It's a series of bars. Now there are a couple rules. Rule number one, everything that is possible that can happen has to have a bar associated with it. Okay? Second thing, you can only be at one bar at the same time. Okay? So you can either have a head or a tail, but it can't be both a head and a tail at the same time. So any event would have been somewhere on the histogram and only in one location. Okay. There's a couple other things. One is something had to have happened, and everything that could happen has to have a bar. And as I mentioned, it can only be in one bar at the same time. And that will lead us to an understanding that if you add up all of the bars, the total probability has to equal 1, right? So everything has to have a bar that it would possibly happen. And when we add them up, they have to add up to 1. You cannot have negative bars. They cannot go down below zero. There is no negative probability of, okay, okay. Probability of Polly getting a tail is not a negative 15%. The absolutely worst case scenario is that a probability. In addition, regardless of what your coaches tell you, there is no probability of being over 100%. Okay. What you will do, you will end up being 100% at most. And when you add up it all together, you get the sum equals 1 or 100%. I just happen to see that Polly has decided she doesn't like me teaching stats without her. Come on in, Polly, come on. We're teaching stats. Come on. Yeah, come on. Yeah, we were just talking about uh, how you play coin. Oh, by the way, this is Polly. In my background, she's here. All right. Now, we don't have to have numbers. Sometimes we can ask the question, what is the probability that a student is male or female? In that case, we will have male, female categories. And at a school like ours, it's pretty close to 50-50, right? But it could be something else. We can draw a that has engineers, business, science, and draw a histogram with the probability of a random student at Tamook in one of those categories. This to have been a legitimate probability distribution, the sum of all those bars is 1, and every possibility has to be there. Okay? So, and there's no negatives. So in this particular case, we probably are missing a few so that we can add a whole bunch of other in it so that we will have ag, gen, ed, who knows what others, right? But essentially a probability distribution is a graph like that, right? Now, this is an example of a discrete probability distribution. And we can have all sorts of stuff in it. I'm going to draw another one real quick. Elliot, don't worry. Not going to get you. We can play this game of flipping, not a coin, but rolling a dice. In rolling a dice, there are 6 possibilities. 1, 2, 3, 4, 5, and 6. Okay. Now, draw that is 1, 2, If my coin is fair, every one of those 6 possibilities have an even likelihood of showing up. In that case, we will call this a uniform distribution, right? But I can draw it this way, which is a uniform distribution with buckets 1, 2, 3, 4, 5, or 6. Or I can also draw the one that I got above it, which is even or odd. In this case, what is the probability of getting an even? Probability of getting an even would be rolling a 2, a 4, or a 6. It would happen 3 out of 6 times. The odds of getting an odd number would be 1 or 5, and also being 3, 6. Again, when our bars are all equally high, we will call that a uniform distribution. Okay. Now let me give you an example here of something that is not a distribution. Six. Last one down on the bottom, okay, is a histogram. It has a bunch of categories. One is 1. The second one is odd numbers. The third one is 3. Fourth one is 4. Fifth one is 5. Sixth one is 6. Okay. The 3, 4, 5, and 6 and 1, each one of those happen 1/6 of the time, right? Okay. The odd number, however, can happen 3 times. Now, why is this not a legitimate? Well, start with, is every possibility there? How about I roll a 2? Is 2 represented? It's not represented as a 1. It's not represented in the bar for odd numbers. It's a 2 is not a 3. A 2 is not a 4. A 2 is not a 5. 2 is not a 6. Therefore, since 2 is something that could legitimately happen, okay, it would need to be on the probability distribution. It is not. So therefore, this could not have been a legal distribution. In addition, when you add up the numbers, they don't add up to 1. 1, 6 plus 3, 6 is 4, 6 plus 1, 6, 5, 6, 6, 6, 7, 6, 8, 6. We have a number when we add them up together more than 1. Okay, so this cannot be a legitimate distribution. Furthermore, it can't be a legitimate distribution because some numbers are in more than one bucket. For instance, if I roll a 5, it will show up as an odd number. It will show up as a 5. Okay, so there's a whole bunch of stuff that's going wrong. So the last one that we have here is legitimate. Okay, all right. With that, we're going to change topics just a little bit. Okay, we are going to put up one distribution that is related to that game that Pollock plays. And in this game, let's say Polly starts with 5 coins. And she is going to dump all 5 of them on the ground, one after each. And then she's going to count how many heads she ended up with after her 5 coins. Right? And she ends up with the following possibility: 0 heads, 1 head, 2 head, 4 head, 5 heads, and 6 heads. Right? These are the various possibilities. Okay. And the graph is actually going to look something like that, right? So here you have an event that's a heads or a tails or a success failure type event that is done over and over and over again. And you count the number of successes. At least counts heads as successes, right? And you will start seeing a curve. It's not a curve, it's a histogram that looks similar to this with different bars. They are not uniform. Okay, there's only one way to get 0 heads, and that is to get a tail, a tail, a tail, a tail, a tail, a tail, and a tail. There's only one way to get all those. Yeah, but there's multiple ways to get 3 heads. You can get them in the first 3 tries, the first try, the fourth try, and the fifth try, the fourth, fifth, and sixth one. You can. There's lots of different ways you can end up with 3. There's going to end up more, right? This particular type of a distribution is called the binomial distribution. And we will give you the formula on Monday. And there's also a table in the back of the book. You figure out this because the math, it's not impossible, but the math gets a little, right? But as we're going to see it in classes quite a bit, there are tables in the back of the book will allow us to come up with this without needing to do it. So this particular uh, discrete possibility is oftentimes called the binomial, and we'll cover that in greater detail on Monday. The next thing that I'm going to quickly cover is I'm going to switch. These were discrete bars, discrete probability. Sometimes we are dealing with things that are continuous. For instance, if you go to the gas station and you pump your gas, okay, it could click off at 6.2 gallons. It can click off at 6.23 gallons. It can click off at 10. It can click off anywhere from 0 all the way to however much your gas tank will hold, right? In every single iteration in there is a possibility. While these we call discrete, these types of continuous distributions. And instead of bars, what we have is a line. Okay? We have many of the exact same rules as we do in the discrete world. In the discrete world, all of these, when we add them together, has to equal 1, right? Down in this world, the area under the chart has to equal 1. So up on top, it's the sum. When we talk about uniform, it's the area. Now, the one that I drew down here, you'll notice it's flat. Everywhere where there's a possibility between 0 and 10 gallons at the same level, and I didn't do a very good job, but it is 0 probability where else. Okay? When we see something like this, where every possibility is exactly the same in that interval, we will again use the exact same words we used before. We will call that uniform. Well, on Monday, we're going to talk about how easy it is to mathematically manipulate and understand what's going on here. But I'm going to leave this for you today. And it looks like it's a wonderful weekend out there. Go enjoy it. And we will talk more on Monday. We'll be back physically in class on campus. Talk to you then. Bye bye.